So good morning. Uh, in the tutorial, we were not able to cover the strong induction. So let me try to use some time to write down what is a strong induction. Okay. So for strong induction, it has so we said in the tutorial that we can treat the statements as a domino, you know. So you have infinitely many statements which is labeled with integers. Okay, so in normal mi, what we do is we prove the first one, and then we prove the inductive step. If the first one is true, then the second one is true. If the second one is true, then the third one is true, right? Okay, so what is strong induction? Strong induction is a little bit different. Our inductive step is as follows. So inductive step, if one is true, then two is true. So it's the same, right? So now you get 1, 2 are true. Now the next inductive step is like this. If 1 and 2 are true, both are true, it implies 3 is true. Okay? So now we have 3 is also true. Now we have 1, 2, and 3 are true. If 3 of them are true, then we implies the 4th of them are true, etc. Okay. So strong induction is a little bit different. So in a normal induction, so we learned that we have 2 steps. So P1 is true, and if Pn true, then Pn plus 1 is true, right? So that's the 2 steps. So for strong mi, we have the following. So we need to prove P1 is true, but at the same time, now if all of the P1, P2 until Pn are true, then so does Pn plus 1. Okay? So you can see that you require more here. So you have more information. So that's why it's called strong mi. Okay? So what's an example? So let me give you an example. So for example, let's say we want to prove for the Fibonacci sequence. Okay, so let a1 equals 1, a2 equals 1, and then we have a n equals an minus 1 plus an minus 2 for n greater than or equal to 3, which is n is an integer. Okay, so now prove that a to the power of n is bigger than 2 to the n. Like this. I mean, probably I can do this. Okay, sorry. Let's do this. Okay. So what is the good strategy? So let's see. So proof. So we need to prove for the base case first. Okay. So here the base case is a little bit tricky. It's not only the P1. See, if you only have the P1, so you will have A1, you can't imply A1 by you can't imply A2 by A1, since this only holds for n larger than or equal to 3. So the base case are in fact P1 and P2. So see, P1 is A1 equals 1 is larger than or equal to 2, 1 minus 1. And P2 is easy. You have A2 equals 1 is larger than 2, 2 minus 1. Easy, okay? So inductive step, we have as follows. Suppose or assume Pn is true for n equals 1, 2 until Pk is true. That's my fault. Okay, from 1, 2 to n. Let me try to write down the statement first. Sorry. So Pk is a statement where Ak is larger than 2k minus 1. This is our statement. Okay. So assume Pk is true for k equals 1, 2 until n. So what can we say about Pn plus 1? So Pn plus 1, we have an plus 1, right? Now, Here, the n we can assume which is larger than or equal to 3. Okay, since like the first two cases are dealt, we can assume this is larger than or equal to 3. And hence, we can use this formula. Okay? But you can see an, we know that it is larger than like n minus 1. And it's larger than n minus 2. And if you like calculate, you have like n minus 2 times 3, which is definitely smaller. Oh, sorry. Oh, it's smaller than. Why I'm making this mistake all the time? Sorry. And hence, you know that this is like smaller than 2 to the power of n. And 2 to the power of n, we can also write it as 2n plus 1 minus 1. I mean, why? Since like here you have like this n, sorry, you have this k, and this k is substituted by n plus 1, so you want to have like this form. And hence, by strong mi, it's done. Okay. There are little details that I have left out, but in fact, like the strong mi is just as this. Okay, so see you next time.